So it looks like it's recording, and hopefully there's sound. I have no idea how to control whether there's sound. Can I see anything?
I don't understand how the Mac works too.
Okay, hopefully there's sound. So this is the folder where we have our classes. So we're going to move on to week 3, Thursday. And of course I want to launch VS Code as well. So this is the code we used last week. I am going to close this one. Or maybe just leave it aside. File, open. Add folder to workspace. And I'm going to add this one. So I have all the files from all the projects so far. All right, so for the third week, I'm going to start the file called collections. .py. Okay. So let's play in the interactive interpreter first. All right. So we looked at pieces of data so far, right? We've seen numbers of various kinds and strings, right? Those were the basic types of data that we've seen. We're going to see actually the string is also a collection in itself. Often that's not sufficient, right? What we need to do is aggregate multiple pieces of data together, right? And that is done using a collection. So typically what we want to have is a list of number or a set of number or a tuple of numbers. And this is what we introduced today. We're going to start with talking about the tuples, which are the simplest ones. And we're going to evolve to lists and sets. And then later dictionaries, right? So there's another one called dictionaries. What's a tuple? You know it from math, right? A pair, a triple, a quadruple. We open a bracket, we write a bunch of things separated by comma, we close the bracket. This is a tuple, right? And you can see that this is a value in itself. This is a collection containing 3 elements, 1, 2, and 3. All right. And if we can assign this to a variable, so we can say collection C equals, and this time I'm going to use strings A, B, C, D, E, F. All right, and we don't have to have all the elements of the same type. So I'm going to just add randomly a bunch of other elements. The tuple can be as long as you like it, right? So by this statement, we have taken this tuple of, I don't know, 7 or 8 elements and named it, given it the name C, right? So whenever we recall the name C, we get the value of the tuple that we have typed in. We can access the individual elements of the tuple by indexing, right? So indexing is done via a square bracket. I can put a number in here and I get the third element, which happens to be 3. I think we've discussed this before. Counting starts from 0. So this is the 0th element, the first, the second, the third, right? The fourth will be 47, right? We can index from the right side of the sequence by using negative indices. So if I say C minus 1, I'm going to get the last element. All right? And C minus 3 will be the third element from the right. So 1, 2, 3. When we start from counting backwards, we count from 1, right? This is minus 1, minus 2, minus 3. All right. For these collections, we have a bunch of predefined operations that we can use in an aggregated fashion. For instance, we can find the length or the size. We can always say len of C, and that will give us the length of the entire tuple. All right. We can extract subsequences. So I can say C from, say, 2 to 6. All right. And I will get a subsequence from the second element to the 6th, actually to the 5th, right? Why? Because sequences are inclusive to the left and exclusive to the right. This is a characteristic that is typical of all programming languages, right? So I count from 2, including 2, up to 6 and not including 6, right? So we're going to have 2, 3, 4, 5 in terms of ranks. We can use, for either of the places, we can use negative indices. So I can do C from 2 to minus 2, and I'll get the same elements, right? 6 is the minus 2 rank, all right? And I can use ranks, negative ranks, anywhere I like, right? So I can say C from minus 6 to 6, for instance. This will give me the same thing. These two quantities are interpreted completely independently, right? I'm going to look at the first one and figure out which one is the minus 6. And I'm going to go and say 1, 2, minus 2, minus 3, minus 4, minus 5, minus 6. So this is the first one, and it's the left limit, so therefore it's inclusive, right? And I'm going to stop at number 6, and number 6 is counted from the left. So this is 0, 1, 2, 3, 4, 5, and 6 exclusive, right? So that element is not included. We can skip elements in the sequence by adding an extra step. So let's say I want every second element in the sequence, right? So I'm going to take 2, skip the next one, skip 3, take 47, skip 6. Yeah. I can take every third element, right? So I can take 2, skip 3, skip 47, take 6, skip 5, skip whatever is left, right? So this is what this means. I can add a step to my subsequence. These are all going to be very useful operations. Now, again, I was saying that there are some operations that work on sequences, on collections at the aggregated level, right? So one was the length or the size, and I need to know that because I wanted to know how many elements there are in there. But we can do things like, for instance, appending. So I can say something like D would be another collection, and let's put here some other numbers: 100, 99, 98, 97, 96. And then I can compute C plus D, right? Which appends the two subsequences. Now, in this operation, neither C nor D have changed. C has the same old value, D has the same old value, right? I can say E is assigned C plus D, and E is a completely new sequence, not sharing any data with either. E is a completely new sequence, not sharing any data with C or D, right? C still has the same value, D still has the same value. Tuples are immutable. They cannot be changed. For instance, if I try to change the value of C4 to say 1000, I won't be able to do that. All right. There is a philosophy in programming which is very much used by functional programming, especially programming with functions, and we're actually kind of following that as much as we can, which says the data should be as immutable as possible, right? So tuples should be preferred to any other type of collection. That's why we study them first. We're going to see that if C is a list, changing an element is allowed, right? So if C were a list instead of a tuple, this statement would succeed. There would be no error and the data would be changed. All right. With a list, we would also be able to update a sequence. So we would be able to take the sequence C, which is this part, and change it to be extended with, right? So the value of C would be changing at that point, right? But so far, tuples cannot change value, so the only choice we have is to create new tuples with values resulting from operations on the old tuples, right? So C plus D can never change, but I can create E with a new value that comes from C and D. All right, is everything okay so far? Yeah.
You said you could change for lists.
Yes.
Could you show the notation or however lists?
It's just square brackets, right? So if I say L is 1, 2, 3, then L is a list. Okay. Then L1 will be 1000, succeeds, and the change is there. Yeah. So this can be useful in certain situations. We're going to explore collections that are immutable before we go to those that are mutable. Cool. So let's try to do some cool stuff with tuples. Before we go there, right? We have another very cool feature of Python, which is called collection comprehension. All right. And in order to talk about that, I have to introduce something, a new type of collection, right? There is a type of collection called a generator. A generator is a lazy collection, right? And the easiest way to have such a generator is to use a range. So let's say I want the range from 0 to 10. This would be the range of all the numbers from 0 inclusive to 9, because 10 would be exclusive, right? So what you see here is not an explicit collection, but it's like this notation, range 0 to 10. And I'm going to call it a range R. And whenever I recall R, it's this range. We don't see explicitly the values. Now I can materialize this generator into an explicit collection. So I can say, for instance, tuple of R. And this will give me the tuple of R. The interesting thing is that once I do that, R has been consumed. It doesn't have any more values inside. It has already been consumed. I can only use it once, right? So I cannot say list R. Actually, I can say list R. I thought I wouldn't be able to say. So, but all right. That's an interesting thing. We can materialize a lazy collection into an explicit one, either a tuple or a list. So R is still the range from 0 to 10. Okay, cool. That's a cool thing. We're going to see this kind of things very frequently, right? And we have to materialize them. Now, let's talk about list comprehensions or tuple comprehensions, collection comprehensions. So you see, I have the tuple of all the numbers, right? I have the tuple T, which is tuple of R, right? T is this. I want all the odd numbers inside this tuple, right? So how do I do that? I will say tuple of all the numbers k for k in T if k percent 2 not equals 0. All right, so I'm just going to run this and show you that these are all the odd numbers. And then let's explain this very quickly. I'm going to start from the end. This is not equal. The history of why this is not equal, why we write not equal this way is very long. It's essentially inherited from a different language, or it's inspired from a different language called C. Actually, I showed you a little bit of C last time. Different languages have different ways of saying not equals. This is the way Python does it, right? We have seen that the numeric equality, or the quantity equality, is this sign. We have commented last time that the simple equal is a way of defining things. It's not a way of checking for equality. This is how we check for equality, double equal. And checking for non-equality is this. Yes? So remember that. Now, percent is the modulo operator. All right? So percent will return the remainder of dividing something by something else, right? Here we divide k by 2, but instead of returning the quotient, which is what division typically returns, we return the remainder. So if we have the number 7 divided by 2, the remainder is 1. If the remainder is non-zero when we divide by 2, then the number is odd. Yeah? It's not even, it's odd. If the remainder were 0, it would be even. All right? And this is like a set notation. Remember that in math, sometimes you say, I want all the numbers k such that, and you put a vertical bar, right? 0 less than equal to k less than 10, and k, and typically you say remainder 2 in math, right? You put something like this, or k, you say k mod 2 is not equal to 0, and not equal would be equal and the bar, right? Not equal to 0, something like that. The equal and the bar would be one on top of the other. Right, so you have this notation for a set. This is what we call a set comprehension. Remember that? Have you seen that before in mathematics? Yeah, so this is a very similar thing, just that instead of the bar, right, we write the keyword for, and instead of this inequality, we write membership in our range T. Yes, this is T. And we filter out the elements. We filter out the elements that are even. We filter in the elements that are odd. So this would be the result. All right. Now, how do I take a range and print all the squares? Very easy. I would say tuple of k for, or of k times k for k in T. Yeah, and I get the squares. Yeah. How do I get all the pairs of numbers between 1 and 10? All the pairs. So now I want a tuple of tuples. Right? All the pairs, so they have to be put in a tuple, but the elements of this tuple, of this resulting tuple, have to be pairs, which are also tuples. Right? Pairs are tuples of 2 elements. So what do we get? We get tuple of I and j for I in T and for j in t, right? So we use the same t, and now what we get is, and luckily my screen width is such that it's exactly 10 pairs per line, so they're very nicely aligned, right? So now we have all the pairs that are possible to create with numbers between 0 and 9. Yes? How do I get all the pairs such as the first element of the pair is always smaller than the last element of the pair? Well, I can use this expression and say if I less than j. Yes? So in this case, I'm going to get fewer pairs. But for all these pairs, whichever I take, you see the first component of the pair, in this case it's 2, is smaller than the second component of the pair, which is 8. Yeah. How do we get all the pairs such that I is less than j, the first one is less than the second one, and the two components of the pair sum up to 10? Right? If I less than j and I plus j equal 10. Yeah, very good. So now we have even fewer of those. All right. Okay. So, for instance, how do we find a solution to the equation I square plus 3j square equals 100? Very simple. I'm going to use this pattern, and I'll say if I times I plus j3 times j times j equals 100. Yeah, and this is the only solution. It so happens. Notice this notation. So this is a single solution, right? It appears to be weird, right? Why do we have this comma here? Is there a reason to have it, or maybe it's a bug in Python? Maybe Python is faulty.
Tuple must have more than one object.
Again, please?
A tuple must have more than one.
Well, that's the thing, right? So it doesn't have to have more than one. It's perfectly legal to have a tuple with a single object. The question is, how do I differentiate between the tuple, the object, and the tuple containing a single object, right? If I write 3 in brackets, mathematically I'm allowed to put any number of layers of brackets around an object. Yeah, so this is just number 3, right? It's like in mathematics. If I say 3 plus 4, it's going to be 7, right? Putting brackets around 3 makes no difference in the value of 3, right? But now, what if I wanted 3 to be a tuple with a single element, right? When I have 2 elements, it's very easy. I put brackets around component 1, comma component 2, right? So the way Python has figured out to solve this problem is to add a comma here, even though there's no second component. So this is now a tuple with a single element. By the way, there exists a tuple with 0 elements. This is very easy, right? I don't have to, right? This is clearly a tuple. There's no reason for it to be anything else. Okay? How do we know what it is? We can say actually type. So I can say type 3, and I'm going to get class int. We're going to see later what a class int is, but int says that it's an int. So if I say this, I would get class tuple, right? It's very clearly a class tuple. If I say 3 comma, I would also get class tuple, right? Which is very clear that this is part of class tuple. If I do not put a comma here, this is class int. So again, I take 3 with brackets around is just the value 3, and the type of the value 3 is int. All right, so we're learning something new here, right? First of all, the solution is a collection of collections. I have multiple pairs being solutions to my problem, right? Each solution is a pair, and the multiple solutions are placed inside another tuple. I need to have a collection of collections. Yeah. Now, sometimes that collection of collections only contains one element. So I have to be able to define the singleton tuple. And this is how we do it. Cool. So now we're going to try to define or solve some more interesting problems, all right, that use collections. So remember last time we talked about generalization. That was a very important thing to learn. So let's see if we can produce a few very simple sequences. So for instance, the list of multiples of a number k smaller than a number m, right? So multiples. So multiples of k smaller than m. And I'm going to say here so that it's clear what we are trying to solve. This is what we call a comment. This is something that Python completely ignores. It is allowed to stay there just to remind us of something, just to inform us of something, right? We can make a note, right? Or I can give you an explanation in that way, right? Anything that follows the hash sign is a comment. All right. Another way to provide documentation to the program is to use the triple quote. So I can say here the same thing, and this is completely ignored by the interpreter. It's actually not completely ignored. I'm going to show you how it's not ignored, but you can think of it as computationally irrelevant. All right, so I'm going to make them slightly different to make sure that. So I'm going to say doc in front, and we're going to see why. So what do we return here? Right, so we're going to start with a range R that is range from 0 to m, yes, and then we're going to return tuple of I for I in R if I %k is 0. Yes? So then let's print a test multiples of 3 less than 100, and we're going to return multiples of 3 and 100. Okay, and Let's just do this a few more times. Multiples of 5 less than 200. Multiples of 7 less than 300. Multiples of 11 less than 200. Okay, 5, 7, 11, 200, 300, and 200. All right, so if we go now and run our file, we're going to get out of here and say Python 3. I'm going to put the minus I. I want to stay in Python after I run this. All right, so notice that the multiples of 3 less than 100 are these. Yeah, we go up to 99. The multiples of 5 less than 200 are these. We go up to 195. Multiples of 7 less than 300 up to here. All right, multiples of 11 less than 200, we go up to here. Yeah. Now, I want to show you something else. I'm going to say help of multiples. What do you see? Can import name DQ from collections. Ah, geez. What is the name DQ? Is there something I didn't import?
What's wrong?
Well, normally I should get this string. Right? So if I run Python 3, for instance, and I say help len, I know why. The name collections is not a good name. All right, let's change the name. Sequences. Let's call it sequences. Not good. Sequences. All right, so now if I say help of multiples, all right, you see this string. Yes? So this string is the string that we have placed here. All right, so help is Python is trying to be friendly. Let's just hide this. Hide this. Hide this. All right, so Python is trying to be friendly, right? And has a help function that extracts the documentation of every procedure that we write, right? Including the predefined one. So if I say help len, you have seen the len procedure, right? We get some help on it, right? So if you bother to provide a help content, a bit of help content for every procedure that you write in this form, then you can access that with the help utility inside the interactive environment. Yeah, so it's good practice to do it, right? This one doesn't count at all, right? So therefore, this is a lot more useful than this kind of command. This can go on multiple lines, so I can say multiples of k smaller than m. This works fine. All right, and if I save it, I can go here, and I can say help multiples, and you see it exactly in the form that we have typed it, right? So if we typed it on multiple lines, you will see it on multiple lines. To get out of here and back into Python, you have to press Q. So I'm pressing Q right now. And then if you want to exit the Python environment, if you're in Windows, you have to type exit. On the Mac, you can type Control D. It's a bit easier. Yes?
Your terminal wasn't showing on.
Again? Why is the terminal not showing? This is because of this. I'm not sure what's going on. It says that my laptop network is performing too slow. Okay, maybe next time I'm gonna bring in an adapter. All right, so sorry about that. Let's repeat the part that, right? So I run. All right, so you get the multiples of 3 less than, multiples of 5. They're here, multiples of 7, right? Multiples of 11. And then if we say help, actually I'm just going to repeat the command multiples, right? You will see exactly the string that was typed in the code. So whatever I have typed here will be extracted here. Yeah. Now, in order to get out of this, I have to press Q, right? Which brings me back to Python. I'm in Python here. And then from here, if I'm on a Mac, I press Control D. On Windows, I can use exit. Yeah. Normally what we want to do is run our programs like this. I just wanted to show you the help. All right, and I was telling you that because of that, right, this kind of comment is much less useful than this kind of comment. This is a lot more useful because it can be accessed by anyone later using help. Yeah. Does this make sense? Cool. All right. How do we get the sequence of Fibonacci numbers? So let's say we want the sequence of all the Fibonacci numbers of n Fibonacci numbers. We want a sequence containing all the first n Fibonacci numbers. How do we do that? Well, Fibonacci numbers start from, say they start from 0 and 1, right? Right? So what did we learn last time? That all these constants are not good. So why say that they start from 0 and 1? Let's say that they start from A and B, right? We get a sequence of arbitrary numbers where I have some arbitrary two numbers A and B, and then every new number is the sum of the previous two in the sequence, right? So we're going to define it as a helper. I'm going to write the helper first, and then I'm going to hide the helper inside, right? But I want to start from the numbers A and B, and I want to print n of them, right? And then if n is 0, we return the empty tuple because a sequence of 0 elements is empty. Yeah. Otherwise, all right, I am going to return else. I am going to return A. So the first element has to be A, right? And I'm going to explain in a minute what's happening, right? So remember what I said last time. If I had the solution of n minus 1, right, how would I use that to create the solution for n, right? So in this case, if I had a solution for n minus 1, I would have to just prepend A, because always A is the first element of the sequence, right? So I would have to prepend A to what? And how do I prepend just one element to a tuple? Well, I create a tuple of one element and I prepend it to the tuple, right? So what do I write here? What's the solution for fib, for helper of, so I'm going to have to write something, and n minus 1, right? I want the solution for n minus 1. What do I write here in the first argument and the second argument?
Is it B and A plus B?
Very good. Very, very good. Somebody who learned the lesson last time. Excellent. B and A plus B. So this is the solution. Very good. Yeah. So this is my helper. And then first I'm going to just show you that it runs. And how am I going to show it to you? I'm going to show it to you by going here and running interactively. All right. So we see the multiples of whatever. And let's nevertheless run the helper, right? So our helper for Fibonacci numbers should start from 0, followed by 1. And let's say I want the first 20 Fibonacci numbers, right? So you can see the first 20 Fibonacci numbers, yeah? Now, obviously, I can start from any other value. I can start here from 100 and 200, but these numbers don't mean anything to us. Yeah, this helper, right, has multiple arguments because of generalization. Without generalization, we wouldn't have been able to solve the problem. Nevertheless, once we have created the solution, the only useful numbers for us are 0 and 1. For this reason, we hide this helper inside another procedure which fixes those two arguments. So I'm going to go here and say, right, so I'm going to have a def Fibonacci sequence, right, and this is going to be the first Fibonacci numbers, right. I never want to start from anything else but 0 and 1, and then this def is a procedure internal to fibcq, right, and I'm going to return helper 0, 1, n. And now we can print a verification, right? Print a test. Print let's do 10 numbers. And we're going to say fib CQ of 10. So if we go here now, we're going to exit, and I'm going to run non-interactively, right? I'm going to see Fibonacci sequence of 10 elements, which is here, right? So this was really good. Perhaps before that, we should have written a sequence of square numbers. So all the squares between 1 and n. So let's define squares. And up to n, right? And we're going to return tuple of all the numbers k for k squared, k times k, for k in range 0, n. Right? So we're going to consider n to be exclusive. And again, let's print a verification for this. I'm going to do another thing. I'm going to separate the outputs. So I'm going to say print, which will print one empty line. Print here also, which will print one empty line. We'll make the we'll differentiate between the outputs. Print the sequence of squares up to 10, and we're going to say squares 10. Okay. This is really simple. Is it clear how it works? Cool. So if we run this, we're going to see the sequence of squares. All right. So another interesting thing that we could do is print the prime numbers. All right. In order to print it, and we're going to do two solutions here, right? One solution would be to generate all the numbers between 1 and the range. Let's say we want to all the prime numbers up to n, and then if they are divisible by any number between divisible between any number. So let's say I want to write a procedure called is prime. I take a number k and I want to return true if k is prime and false otherwise. All right? So how can we do that?
Use the percentage operator.
Yes.
Check if that's equal to 0 or not.
How do we generalize this? Let's think of a general. When is a number prime?
When it doesn't have any other factor other than 1 in itself.
When it doesn't have any factors other than 1 in itself, right? So it means that it is not divisible by any numbers between between 2 inclusive and itself exclusive, right? Actually, we don't want, let's skip that definition. Well, you don't have to go up to the number itself. We can go up to just the square root of that number, right? And I can explain that, and that will optimize the search. But for the time being, let's just take all the numbers between, so if I want to say, for instance, if 11 is prime, I have to check whether it's divisible by all numbers between 2 and 10, right? Yeah, so now 10 is 11 minus 1, right? So 10 is a limit that is dependent on the number, right? But the first limit, 2, is a constant, right? And we learned when we want to solve these problems that constants are not good and we want to generalize. So we're going to say, well, why start from 2? Let's start from an arbitrary number. Right? So my helper is going to check whether a number k is divisible between the limits j and k minus 1. Right? So I'm going to write a helper here, and I'm going to say is divisible by all numbers. This actually should be just a helper, but let's call it is divisible so that it sort of has a meaning between all the numbers between j and k minus 1. We already know what k is, so I don't have to worry about that, right? So I don't have to put a k here, right? K already exists here. So is divisible by all the numbers between j and k minus 1, right? How do we check that? Actually, what I want is not divisible. I don't want the is divisible, right? Because I want to lead to a prime, right? So I want that k percent j is not divisible, means not equal to 0, and is div between k plus 1 and j, right? Sorry, j plus 1 and k, right? We don't have to say that. Now, this is true as long as j is smaller than k. Yes? But we have to look at the case when j is greater than k, j greater or equal to k. So if j is greater or equal to k, we're going to return true. Else, we're going to return the value of this, right? So you see this helper, it's a generalization. Instead of looking at divisibility between 2 and j minus 1, we're looking at divisibility between 2 and k minus 1. We're looking at divisibility between j and k minus 1. Because we have generalized, now I can go from j to j plus 1. Yes? And then if this returns true, let's call it is not divisible. Because that's what we're looking for, right? Non-divisibility. So if this is true, it means that there's no divisors. Yes, please.
The last function, id not, is that supposed to be is not?
Is, yes. Good catch. Very good catch. Is not divisible. Right? So what does this say? Right? Are there any divisors between j and k minus 1? Right? If j is greater than or equal to k, that's true, right? Otherwise, check k and then check every number greater than j plus 1. Right? Is this clear? So now we're going to be able to say that when do we know whether a number is prime or not? Is not divisible starting from 2. Yes? If it's not divisible starting from 2, then it's prime. So let's see if this works. So print is 11 prime. So the answer is going to be true or false, right? And let's keep going. 37 prime. $51. Right, what else? 97. Yeah, so we can run this now. And is 11 prime true? Is 37 prime true? Is 51 prime false? Is 97 prime true? Yeah, these are well-known prime numbers, so it's very clear. This one is clearly not. It's divisible by 3 because 5 plus 1 is 6, which is divisible by 3. Cool, right? So we know how to check whether a number is prime or not. Now, if we want the sequence of prime numbers, and I'm going to say 1 because it's the first solution, of numbers up to n, how do we solve this problem knowing that we have this solution now? Come on, this should be very easy. Return tuple of all numbers I for I in
The result is true.
I haven't gotten to the true. This prime is not a way to. This prime is something that returns true or false. When I say for I in, here I have to put a collection. Right? Here I have to add in an expression that evaluates the collection. Right? So range 0 to n, right? So I cast a wide net. My prime numbers are somewhere between 0 and n, right? So I'm going to cast a wide net. I'm going to generate a collection that is bigger than what I need. And then I'm going to filter out if, and now is the true part, if louder is prime of I, right? So this is it. This solution is not very optimal. It's quite wasteful in terms of computation, but nevertheless, let's do a test. So let's print here an empty line, and then let's do print lower than 100, and we're gonna say prime CQ 100, and let's see what kind of answer do we get. Right? Range from 2 to n. We can't look for primes in 0 and 1. Yeah. So these are the prime numbers. So this is a relatively simple strategy for solving problems, right? I find a way to indicate whether this is my number or the current number that is being tested is part of the solution or not. Then I cast a wide net, and I filter in only the numbers that are part of the solution. Yeah. Okay, let's try to find a more. And the computer is so fast, you will only see that it's becoming slow if I use a very large number here, right? So just out of curiosity, 1,000 will still be not very large. But we get too much recursion, right? So let's do 500. But we will still not see a slowdown, right? So it still goes quite fast. If I go to 9, 4. Okay, yeah. So 995 is actually the limit where it blows. So I can get all the numbers lower than 991. Now, something that is a bit faster, though we won't necessarily see it. Okay. So again, we want to look at the sequence of prime numbers in a holistic way, right? And I want to generalize. This generalization is going to be a bit more tricky, right? So I want to be more targeted this time, right? So instead of starting from 2, always when I say the list of k primes or n primes, I have to start at 2, right? And 2 is a constant. Why should I start at 2, right? So I want to start at a different number, right? So what should I be looking for, right? So I'm going to be looking for the list of numbers between n and m such that each element in the list is not divisible by another element in the list. This is a little bit strange, right? But let's say I'm looking for numbers between. So I'm looking for a solution where n and m is 10 and 20, No, let's 10 and 50. Yeah. So the first number should be 10. As soon as I put 10, all the numbers divisible by 10 cannot be in the list. 20, 30, 40, 50 cannot be in the list, right? Then 11 is okay, right? All the numbers divisible by 11 cannot be in the list, though, right? So I'm going to go to 12, 13, 14, 15, 16, 17, 18, 19, 20 cannot be there, right? 21 is okay. 22 cannot be there. It's divisible by 11, right? 23 is okay. 24 cannot be there, yeah? 25 can. 26 cannot be there. 27 can, yeah? And so on and so forth. So I can only pick a number here that is not divisible by any of the previous numbers, right? When I say it's not divisible by another element in the list, well, divisible is always smaller numbers, right? So it's the preceding numbers that I have to worry about, not the succeeding numbers, right? But it's very clear how I can create a list that has this property, right? I start at 10, I want to go up to 50, right? I write 10, I will exclude all numbers, all the multiples of 10. I write 11, I will exclude all multiples of F11, and so on and so forth, right? So I'm going to go like this till 25, right? 25, 50, which is part of, let's say it's part of my list. 50 cannot be in the list, actually, even though it's a limit, because 50 is a multiple of 25, yeah? Now, very interestingly, whenever n is 2, this list becomes what?
Odd.
Not just odd. Becomes the list of prime numbers. Yes? Between lower than m. So if n is 2, this list automatically becomes the list of prime numbers, right? So what have I done? I have generalized my problem. This is the new statement where I can recover the solution that I want, all right, by setting n to 2. So I'm going to write a solution to this problem. This is going to be my helper, yeah? So def, this is going to be prime, let's just call it primes, up to n, and I'm going to have a helper going from m to n. Let's go m and n. Alphabetically, m is before n, so we should respect that, right? So now if m is greater than n, return the empty tuple, yes? Else, I'm going to return what? Well, the solution always starts with m, right? M is the first number. I always start with m. So I'm going to have m as a tuple plus, right? And now the question is, if I have the solution for a shorter interval, when do I have a shorter interval? Well, m plus 1 to n is a shorter interval. Yeah? So previously, we say the smaller solution, and we go from n to n minus 1. Here, we have an interval from m to n, and if I go from m plus 1 to n, my interval is shorter, right? So m plus 1 to n is actually a shorter, a smaller solution. So if I have the helper from m plus 1 to n, right, how does this one help me produce a solution to everything? Well, what may this one contain that shouldn't be part of the solution? It may contain multiples of m, right? So I'm going to say tuple of all the elements k for k in helper for k in this smaller solution, for k in this smaller solution, if, right, k percent m is not equal to 0, right? So I'm going to put this here so that it's easier to read. Does this make sense? So I have the smaller solution, and I'm trying to use this to go to the bigger solution, the solution that starts at m, right? So in order to create a bigger solution, first of all, I have to prepend m, because my list always will start with m. And then this smaller solution, what may it contain that is not part of my solution, of the bigger solution? Well, those multiples of m. So we simply filter them out. So this is the helper. And if in this helper m becomes 2, then I have my primes. So return helper to n. Now it turns out that this n is the same as this n, is the same as this n. So I don't have to put it here actually, and consequently I don't have to put it here. That makes for a simpler, somewhat solution. Yeah. But if you have trouble figuring this out how it works, feel free to leave the n here. Okay? So, let's do a up to, let's write up to here so that it's different. And let's run this. Yeah, so one thing, whenever we break lines like this, we need to do one of two things. Either put brackets, this is the more natural solution. So Python will understand that this is not the real end of the expression. Or, which is what more experienced users do, we can put a backslash here. And that allows us to go to the next line. This is considered very ugly, all right? But it's actually the recommended solution. So now we can run, and I need to remove the n here as well. And we see that we obtain the same solution, right? Now, if we would run this for very large numbers, we could see that this one is faster than this one. Okay? Yes?
Okay, what does the backslash do?
Simply allows you to continue a line. Python is a language where lines are important, right? Lines and indentation are important, right? So it will always try to assume that this is a complete statement. And obviously a complete statement cannot end with plus, because an expression is something plus something else, right? And the way to indicate that, oh, this is not the actual end of a line, I just didn't have enough space, and I wanted to continue the current statement on the next line, is by placing a backspace here. If you have trouble with that, you can drop the backspace and just put brackets. Will accomplish exactly the same result. Right, this works fine. Does it make sense? All right, this is what I have for today. Questions? Yep.
When you say we need to generalize, you just mean that we need to define it for arbitrary quantities, so that it's not like.
Yeah, whatever is a constant, why should it be a constant, right? Well, I'm saying all the primes less than x, right? This means automatically I'm starting at 2, right? Why start at 2? Let's talk about all the primes between y and x, right? And then that actually is easier to solve. Even though it seems that I have introduced more unknowns, it's easier to solve than the one that has more fixed values.
What is the purpose of the generalization? Lesser computation, or is there something else?
So in this case, there's no other solution. No, I mean this is actually a more elegant solution than the one given before. Yeah, this is what we call the sieve of Eratosthenes, right? Whereas this one is this is a brute force solution where we test a lot of numbers unnecessarily. Yeah. Cool. If you want to stick around and have more questions, feel free. Otherwise, class dismissed.